Hello, everyone. Uh, Today I'll be talking about our work named CFDLLMBench, which is a benchmarking suite for evaluating large language models in computational dynamics tasks. So, why we need a benchmark LLMs for CFD? So, CFD is a very labor-intensive task. It requires a lot of knowledge of the domain. Then it requires, some code execution, some writing codes, maybe understanding some complex softwares, etc. And all in the essence to discover something from a fluid dynamics perspective. And LLMs have shown that they are very useful in automating things and understanding complex physical systems, etc. But still, a lot of the capabilities in fluid dynamics domain is underexplored. So here we would like to look at the intersection of LLMs, which is test generation, machine learning, etc., and and look at fluid dynamics, which basically involves some governing equations, flow physics, experimental data, etc., and look at the intersection where we have very interesting tasks like generating codes for solving certain problems, automating a simulation setup, automating simulation softwares, data-driven discovery, etc. So, so what we are trying to do here is that trying to evaluate if the LLMs which really excel in NLP do they do very well with physical reasoning, understanding the physical laws, etc. So here we used a three-pronged approach in evaluating the LLMs. So we have three separate data sets within our benchmarks. And first one is named CFD query. And CFD query is all about evaluating whether the LLMs have the theoretical knowledge. So it has 90 graduate level multiple choice questions, and the LLM is asked to choose a right option, from that. And And then going to a higher stage of complexity is CFD Code Bench, where we have 24 programming tasks for Python code generation. So here, given a prompt, for example, to solve a PDE like viscous burgers, as we have an example here, we give all the details like the boundary conditions, the initial condition, etc. And the idea is that we ask the LLM to generate a Python code which would solve this PDE under these given conditions. And the LLM should generate an executable, accurate Python code. And going into the highest level of complexity is we have FoamBench, where we evaluate not just LLMs, we evaluate agentic systems that use LLMs in orchestrating a complex simulation software like OpenFOAM. So here we have 126 prompts which describe OpenFOAM simulations. And the LLM's task is to use these prompts, use an agentic system to create agentic system which already existing to create required OpenFOAM input files and run the simulation. And we evaluate how accurately the agents create such simulation setup based off the prompt. And next up, we show the dataset composition in each of these benchmark tasks. So in CFD query, we look at linear algebra, numerical methods, fluid mechanics, and other generic questions. In CFD code bench, we have questions related to compressible flow, incompressible, linear, nonlinear PDEs. And FoamBench, we split it into two data sets. One is called FoamBench Basic and Advanced. And in Basic, we use some tutorial problems that encompasses laminar internal flow, turbulent flows, multi-phase flows, buoyancy, etc. And these are extracted from existing OpenFOAM tutorials. And we have around 110 cases. And to make things a little bit more difficult, we have FoamBench Advanced, which are not present in tutorials. They are not available to any of the LLMs prior. And these are cases which describe a much more complicated geometric scenario or a physical scenario that requires actual understanding of the LLM, actual understanding by the LLM to solve these issues. And for evaluating, we use a metric which is called as a success rate. So, and which is defined differently for these different tasks. For CFD query, the success rate is defined as number of correctly answered questions by the total number of questions. Straightforward. And for CFD code bench, we look at 3 individual metrics and their combined effect. So we have something called as a case is supposed to is successful only if the 3 metrics are turn out to be true. That a metric which executable, which basically goes to a value of 1 if the code executes without any syntax error. And next metric which needs to be satisfied is the MNMSE. The MNMSE will be 1 if the normalized mean squared error is less than 10%. And normalized mean squared error is nothing but you take the mean squared error divided by the square of the value, the final results of the Python code that is being generated, and look at its value. And if the NMSE is less than 10%, if the MNMSE metric becomes 1, and if it's between 10 to 30, it becomes 0.5. If it's 0, if it's greater than 30, it's 0, meaning that the generated solution is not very accurate with respect to some ground truth we have. And then finally, we have another metric, M convergence, where it is as we increase the number of grid points, the solution error needs to come down. And if this property is not satisfied, then we don't call it solution as convergent, and this metric goes to 0. And if it's convergent, this metric is 1. And success rate is defined. So a case is defined to be successful if the executability, NMSE, and convergence all have a value of 1. All these metrics have a value of 1. And the success rate is again defined as a total number of cases where it's a success divided by the total number of cases. And in CFD, in form bench, we define the success just in terms of whether it's executable, whether the agentic system is able to execute the open form simulation without any syntax errors, and if the NMSE is less than 10%. And if this is the case, we consider that case as successful, and we calculate the success rate as total number of cases which was success divided by the total number of cases. And if you look at the performance of different model, you can see this plot explaining the success rate with for different models like Sonnet 2.5, O3 Mini, Gemini 2.5 Flash, etc. in the different tasks. So you can see that in CFD query, which is supposed to be like a theoretical question and answer task, all models do really well, close to 91%. But as you go to more practical scenarios like code generation and an agentic system demonstration, you can see the model struggling. So in CFD code bench, the best performing model can only do as good as 14%. And in form bench, you have both the basic and advanced. In basic, the highest success rate is around 34% for Sonnet 3.5, and in advanced, it's around 25%. So you can see that there is a huge gap between theoretical knowledge and actually executing physically relevant workflows that produces useful results for scientists and engineers. And next up, we look at we do a deep dive, of these metric scores for CFD code bench. So in CFD code bench, we discuss that we have different metrics like executability, NMSE, and convergence, etc. And finally, the success, when all 3 aligns up. So you can see that in most models, you can see they have good success. The code at least executes like 60 to 70% the code executes. But then are they accurate? Maximum only like in the best model O3 Mini, only in 40% of the cases, you'll see the code actually being numerically accurate with respect to the ground truth. And then if you look at if the code is convergent, the ratio again goes down. So, and the overall together, you can see that it's around 14% for even the best performing models. So this basically shows that if holistically viewed, the LLMs do not do a great job in solving in these practical code generation tasks. And then we look at agentic systems for OpenFOAM, for which we developed FOAMBench. So first of all, why do we need agentic systems? Why can't just we have an LLM generate all these input files for OpenFOAM and then just run it? But if you look at, were to do a zero-shot prompt, just provide an LLM with these prompts and ask it to generate the files, you can see the success rate in FOAMBench Basic is like around 4.5%, and FOAMBench Advanced is close to 0%. Hence, we need an agentic system so for carrying out OpenFOAM simulation, and we evaluate two agentic systems. One is Foam Agent and Meta OpenFOAM, which are the leading two agentic systems. And and then if you look at the agentic system comparison, so we have different combinations, and these agentic systems have components like RAG and a reviewer, etc. So RAG is basically a database of example or tutorials, and reviewer is a agent which looks at the execution errors and try to correct it. So we do a variation of the combination of RAG and reviewer, RAG with no reviewer with RAG. And the best performing combination is having both RAG and reviewer, which for Foam Agent gives a success rate of 34% in basic and 25% in advanced. And we do also, for bookkeeping, we look at similarity metrics, typical NLP similarity metrics, like file similarity, because the agent system generates files which we compare against ground truth files, and we look at how similar they are. So you see the file similarity is like around 70%, and in execution success rate is around 80%. But then file similarity misses out on whether the simulation is actually running and if there was any numerical error in the simulation, and which is ultimately reflected in the success rate. So we see that our definition of success rate is a much more holistic view of if the simulation was success or a failure. And you can see Meta OpenFOAM doesn't perform as good as Foam Agent in both the tasks. Meta OpenFOAM success rate is around 13%, 12 to 13% in both basic and advanced, and Foam Agent performs much better. So in conclusion, we propose CFDLLMBench to serve as a test bed for the next generation of scientific LLMs. So our view is that the benchmark that we created takes a holistic view to cover the different spectrums of CFD competencies we evaluate for an LLM. And we hope that it would serve as a future test bed for the upcoming LLMs. And some of the next step is to include a human baseline and expand it to other domains like solids, materials, etc.